Okay, perfect, yeah. So all I was missing here is, all I was missing here was was a negative on this exponent. So let's go back. Yeah, all right. So let's just test this out briefly. So the temperature, when the time equals 0, equals T infinity, 1 minus e to the 0, right? Because if time equals 0, that's 0, equals T infinity, 1 minus 1 equals 0. And that's in fact what it equals right there. At time equals 0, the temperature 0. And this is really the change in temperature, right? So it's not that we're at absolute 0. It's just how much the temperature has changed. And when you initially stick the thing out there, it has not had time to change its temperature yet. Now let's look at it at infinity. So delta T at time equals infinity equals T infinity 1 minus e to the negative infinity. Doesn't even matter what that other number is down there. Equals T infinity. Anything to the negative infinity is 0, so 1 minus 0 equals T infinity. And that's where you're heading. So I would like you also in your theory section to include this equation. And and you have two variables in there. One is the steady, and T infinity is just the steady state temperature. At some point, I think you guys have seen in your notebooks, it's just not getting any hotter, right? I mean, it reaches a point, it's just like, so your data, believe it or not, when you start to plot it, will look like this. So you should be able to just plot it out, and you'll see, okay, here's an X, 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 X. And then once you have that, you can go back and use your summary 3 skills, put that in, and ask Microsoft Excel to tell you that number, that time constant. Because we got those time constants already with our population dynamics. There were two numbers that popped out. Tau. Tau is just the Greek symbol for time, and it's just an easy way to know that you're comparing apples and apples, basically. I mean, they're both measured in seconds, but I think what you can see here is that if tau is small, your temperature is going to rise really quickly, and that would be the case if you had a small technology. If you had really nice insulation, that temperature is going to pop up really quick. If the thing's really big and takes a long time to heat up, think of it like an electrical circuit. And in fact, that's where this equation came from. It's an electrical circuit. And this C right there is capacitance. If that capacitance is really big, if you had some gigantic system, it's going to take it longer to heat up. It's going to be a bigger time constant. And you would get something like this. So I'll just say this is going to be tau, greater, let's just say much greater than 1. And this other curve I drew up here is going to be tau much less than 1. Make sense? So big thermal capacity, temperature's going to change, small thermal capacity, temperature's going to change really quickly. Big thermal capacity, Tromwell kind of thing, Manhattan Island, it's going to take longer for that temperature to change. So that's what that tau, that's exactly what that tau is. It's telling you how long it takes to change. Just like the capacitance in a circuit. Yes?
All right, so I'm struggling to understand. So just on the X and Y axis right here.
Yeah.
The most simple part of this whole
Yeah. Yep.
This is temperature difference.
Well, this is going to be 9 a.m. right here. This is going to be 10 a.m., 11 a.m., whatever. That's just time measured in hours. And this is temperature measured in Fahrenheit, Celsius, Kelvin, Rankine, whatever, degrees. Kelvin's doesn't get degrees. Rankine does. But what are you guys using? Fahrenheit or Celsius? Yeah. So this stuff so that this stuff works out, you're gonna want to use Kelvins or Celsius. Don't mix your imperial units with your SI units. Does that make sense? This equation is a little bit complicated, but if you just plot it in Excel, you'll get that curve. Let's just try it. I'll knock it out really quick. Not a big deal. Let's knock it out. All right. Let's just start. Let's just go 1 to 10, and now we'll make. So that's time. I'll put it in seconds, and here's going to be temperature, and this is going to be in Celsius. And now I'll put over here. I'll just put. I'll put T for temperature. Infinity. Put that as a subscript. And I'm just going to throw 110, let's do 110 Celsius up there. And what you might even do here is put in a little time factor. And I'm just going to call it 10 for now. And I can take this guy and do, and I'll write this time factor. Subscript. So I'll say this equals that number times this number, and I'm going to put a dollar sign in there to pin it. So now you can see that I can actually mess with that whole column right here. Right. So if you guys are taking your times at different intervals, you can just put the number of if you're taking the 30-second intervals. Now you can tweak this chart very quickly to whatever your actual data is. Do you see how I did that? And I just put these in as just regular old data points. You're like, oh shoot, man, I can't use 1 through 10. I gotta put it in. Right? Clear? Yeah, Lance?
T is that's used.
T infinity. We're getting to it. Yeah, we're going to get to it. Your initial temperature. So these are just going to be temperatures that you measure. So let's just say you walk out there, and it's going to be 25 centigrade. Then it's let's just say 20. Let's just ramp it up. Then it goes to 35. Then it goes to 44. Then it goes to 53. Then it goes to 62. Let's just say 71. I'm kind of making these up. 80. And it starts to slow down. 85. Now let's go to 80. 6 something. 95. 110. Something like that. That's just your raw data. So I'm going to go in here, insert charts, chart. Okay. And I'll go back and say, I probably should change that up. Let's just go 38. Let's take this guy. Actually, let's go up even a little further. Let's just take that to 40. Nah, let's take it up even higher. Let's just go to 50. I'm gonna artificially make a exponential. 77. And I'm thinking your data will probably look something like this. 95, 100, 105, 107. So that kind of looks like an exponential. So I'm guessing your data is going to look something like that. Now, remember summary 3, right click, add trend line, exponential. Display equation on chart. Oh. And it was not ready for what I tried to throw at it. Yeah, it's got just a regular exponential instead of the opposite type. Okay, that would have been a problem. So let's back up for one quick sec. I think I can fix that. It's not gonna be immediate, but let's look at it this way. So so this is my data right here. I'm going to write my theory out here. And what I'm going to do is put in, I'm going to put in T for tau. And I'm just going to, for now, let that be 10. So the only two variables in this equation are this one number up front and then that time constant tau. I'm going to take that guy and change it into a symbol. So now it's a tau instead of a t. Center that up. Okay. So now this is going to be equal to t infinity times open paren 1 minus exp negative t for time divided by time constant. Oh, I know why. I've got to have, please don't try to help me. Thank you, though. The exponential needs to be a function. There we go. E to the negative. Got to have that negative in there. A $3, a $6. Boom. That went better than expected. Okay, so now you can see that in the theory, again, let's just go back and review this equation. So there is, the very first part is a $3, so that's our T infinity, it's labeled right there, times 1 minus, exp is the function for the exponential function, exp, and in that exponent is negative t, so that's what's in the cell E3 right there, divided by the value in A6. and A6 is our time constant. So you can see with that, with the T infinity, with the time constant, and with the data, we were able to recreate an exponential. Lance, yes?
So what is,
What is
E?
this thing right here, E?
Yes,
This E right here?
yes.
Oh, this guy. Oh, E is the second most famous number in mathematics, was after pi. So, E, it's not entertainment. It's the exponential function. And it's just, it comes into play all over the place, just like pi comes into trigonometry. So E is very special in that the exponential function, which is right here, that's the exponential function. Special thing about it is that whatever its value is the same as its slope. So the bigger the number gets, the faster the slope. And that's why, I mean, a little bit of a segue, but that's why there's a whole bunch of rich people in this country. Because if you're working on, if you're working on 10% interest rates and someone else is working on 4%, their money goes up that much faster. So it's like the more you have, the faster it grows. That's the exponential function. And as it turns out, it's just a number, just like pi is just a number, 3.14. E is 2.71, etc. So there's kind of an interesting little, well, I mean, there it is. You know, some people memorize pi to the 10,000 digits. Same thing with E. So that's all it is. Just, number. Okay. So what we can do now, and I see why this. And again, I don't know. If you guys get this far, let me know, and I can show you how to flip that number over so that the function in Excel actually works the way we want it to. But if we come into this plot now and we say select data, let's go in and add, and let's add theory. The x values are simply the times. The y values are our prediction. So that's pretty good looking right there. And I can go back and fix that exponential here in a little bit. But so now you can say, well, gosh, that's not too bad. My theory was pretty close to my data. So in your background research, and we actually did a little bit of solar thermal background research. I'll guarantee you there's some paper out there that's got a very similar technology to yours, and it's going to plug in. Okay, here's what the colors are, et cetera, et cetera. There's almost certainly some theory out there where you could predict the performance because you've got your data. And just one more thing on the theory, the proper way to do this would be to would be to get rid of the marker, because otherwise it looks like you were taking those data points along there. So the proper way to do it is to leave your points on there as data points. You could make them X's or open circles or whatever, but leave the theory as just a line. Is that clear? Okay. I think I might play around just a little bit. I think I can get that other curve to bend the other direction if I just do this. Let me try. So I'm gonna try this. Data minus 1 equals 1 over d. Nah, it's not working either. There'll be a fancier way to take that exponential that's climbing and then slowing into one that's accelerating, and I'll have to look at that for a little bit, but, so is that a good, I mean, I think that's, so again, just to review, what I'd like to see is in your theory section, I want to see your overall efficiency, like so. That's your efficiency. And then do include the losses so you can measure that with your kilowatt meter, and that way you'll have a nice set of data. And please also, take your best shot at predicting this. Remind me, I'll give you Armistad's paper, because he did a nice little prediction on, for example, how long it takes to heat your house. Because that's at the end of the day, that's what people care about. And that's the nice thing about these renewable technologies is they're relatively inexpensive to build, but they're not. It's not like on-demand heating, right? You're not going to snap your fingers and get rid of the cloud or make the sun come up. That's really the one downside compared to the conventional fuels. But knowing this theory, you'll be able to then predict how this could work as a supplement to a conventional system. Good? 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 Okay, thanks.
You've read it. Just curious.